Hello calculus fans, and welcome to section 2.8, which covers the derivative as a function. So section 2.8 is a lot like 2.7. We just make a little bit of a change. So in 2.7, we consider the derivative of a function at a fixed number a. So you would have this derivative at, say, 3 or something. We'd find f prime of 3. Or maybe we'd find f prime of a and then plug 3 into the answer. But a was always a constant. Now what we're going to do is we're going to let a vary. So we'll replace a by a variable, x. And that gives us the limit definition of a derivative, which you can find in any calculus textbook anywhere, which says the derivative of a function f of x with respect to x is the function f prime of x defined as, right here, the limit as h approaches 0 of f of x plus h minus f of x all over h, provided this limit exists. So if you're in one of my face-to-face classes, on a test, I'll always say something like state the limit definition of a derivative, and we really, if you're in my face-to-face class, we'll have to, one of the questions on the test will be this right here, and this is what you'll need to state. And because it is a limit definition, of course, we need a limit, and basically just looks like just like this. This is what we would need. So a little note here, f prime of x is the derivative of f of x. The derivative of f of x. So geometrically, f prime of x gives us the slope of the tangent line to the graph of f of x at this particular point, right? And we talked about that before. The derivative geometrically gives you the slope of the tangent line to the curve, right, at this particular point. So if you wanted to know the slope of a tangent line to a curve at the point when x is 4, you just take the derivative and plug in 4, right? So let's see how that works. One thing to keep in mind is that in section 2.7 and 2.8, we do a lot of algebra and limits to find these derivatives. It's kind of a lot of work, as I'm sure you're aware. But in chapter 3, we're going to find shortcuts for all of this. So some of you who may have taken calculus before probably remember the power rule for the derivative, and you can find the derivative of this really quickly, just less than a second you can have it. But we have to learn initially this limit definition of a derivative, because underlying all of calculus are these limits. So we'll go through kind of like the hard way first. We'll learn how to do this using the limit definition of a derivative, because that's really how they're defined. And then later in chapter 3, we're going to learn a lot of shortcuts. So let's take a look at this one. So we want to find f prime of x. So f prime of x, well, by the definition above, it's going to be the limit as h approaches 0 of f of x plus h. So remember what that means, f of x plus h. I look at this, this is f of x. So wherever I see an x here, I'm going to replace it with x plus h. So it's going to look just like this, but wherever there's an x, I'm going to swap it out with an x plus h. So that would be 3, not times x squared, but times x plus h squared, minus 5, not times x, but times x plus h, and then plus 2. So right here we've got f of x plus h, and then according to the limit definition above, we have to subtract f of x. Well, f of x is right here, so I just subtract this. You just have to remember one thing. I'm going to make a mistake right here and see if you can catch what's happening. 3x squared minus 5x plus 2. If I do this, it's not going to work. So what am I forgetting? Well, when I subtract f of x, there's 3 terms here, so we're going to need parentheses, right? We need these parentheses so that we can distribute that negative through. And then this is all over h. Now, if you were to take the limit at this point, as h goes to 0, we're going to end up with a 0 over 0. So what we have to do, this will be very familiar because we did pretty much the same thing in 3.7. We just would have an a here. But we just had to expand this, and we'll see that anything that doesn't have an h should cancel, and then we should have terms with all h's, and then we can cancel the h's. So let's see what happens, see if it works. So remember this one, x plus h squared. I think I need to make me a promise that if you ever have something like x plus h squared, promise me you'll never do this. Makes me very sad when I see that, because remember, we have to take two of these binomials, right? Line them up next to each other and multiply, so we need the FOIL method. So this is just not going to work. You don't want to ever do that. If you do that, you'll feel very sad. So we need to expand this, right? So when I do this, I have 3, and x plus h times x plus h is going to be x squared plus 2xh plus h squared. Then I'm going to distribute the negative 5 through, so I get minus 5x minus 5h plus 2. And now we'll just distribute this negative through. So the negative will come through here, and we'll get minus 3x squared plus 5x minus 2 all over h. And now we're almost ready. We just have to take this 3 and distribute it through here. So that will give us the limit as h approaches 0. And I know this is kind of tedious. We keep writing all this, but we have to write that, right? We have details are going to really matter in the careers that you're going into. If you're going into a STEM field, you're taking calculus, details will definitely matter. So it's good to use good practice right here and just use these limit definitions the way they're meant to be, and just expand this through. And let's see, hopefully when I get done writing, we'll get a bunch of things to cancel. All over h. Okay, let's look what we've got here. 3x squared minus 3x squared. And let's see, minus 5x plus 5x plus 2 minus 2. So it looks like everything that's left has an h in it, right? Limit as h approaches 0. 6xh plus 3h squared minus 5h all over h. So we still have 0 over 0, but we have an easy way out now. Every term, there's 3 terms up here, 1 down here, they all have an h, so we could cancel an h out. Cancel that h, cancel one of those, cancel that h, cancel that h. And we get the limit as h approaches 0 of 6x plus 3h minus 5. Now we can take the limit. This h will go to 0 and send that whole term to 0. So we've taken the limit and we get 6x minus 5. So f prime of x is 6x minus 5. So remember how we can interpret this derivative geometrically as this is the formula for the slope of the tangent line to this curve at any point x. We just have to plug it in. So if somebody says, you know, what is f prime of 2? What is this thing? Well, f prime of 2 is going to be the slope, the tangent line to that parabola, 3x squared minus 5x plus 2, at the point when x is 2. And to determine what it is, we just plug in a 2 here. So 6 times 2 is 12, minus 5 is 7. So f prime of 2 is 7. That means the slope of the tangent to the curve at the point when x equals 2 is 7. So here's a picture of this. If this is that parabola, the parabola 3x squared minus 5x plus 2, and if you go to where x equals 2, so where x equals 2, and then if you go up and measure the slope of the tangent to that curve, the slope of the tangent at that point is 7. So basically this gives the formula for the slope of this curve at any point. Just plug in whatever x value you want, and it gives you the slope of the tangent line to the curve at that point. Just one more time, I want to just emphasize this point here. This derivative gives us the slope of the tangent line to the curve. So you can think of geometrically, when you think of derivative, think of slope of the tangent. Derivative, slope of the tangent. So let's say you're driving in your car today and you hear somebody on the radio say derivative. What should you think? Slope of the tangent. Derivative. Did it work? Did you think slope of the tangent? Hopefully you did. All right, let's move on. Okay, so one thing we'll have to be able to do is a problem like this, where they give us the graph of a function. So here's y equals f of x. It's this function that goes like this. And then what they're going to say is use this to sketch the graph of the derivative, f prime of x, and the second derivative, f double prime of x. So the derivative f prime, if I sketch that down here, the derivative, you can think of it as just the slope, right? The slope. So if I wanted to know the derivative of, let's say, this function when x is right here, whatever that x coordinate is, well, the derivative is just equal to the slope of that tangent at that point. So if I were to make this graph be y equals f prime of x, this is basically a collection of slopes of this curve at each point, because it's the derivative geometrically is equal to the slope. So if I could like measure the slope at each point, so let's say I measure the slope right here. Let's say the slope is 1. Now there's no units here, you know, these axes aren't scaled or anything, but let's just say for the sake of argument, let's say the slope at this x coordinate is 1. So I would go down to that x coordinate and put a dot at 1, right? Because this is going to be the recording of all the slopes of this curve. So let's say this x coordinate right here, this x coordinate right here on the x-axis. If I go up and I measure, okay, and let's say the slope of this thing is -7 or something. So then I go to that same x coordinate, I go down here and I put a dot at -7. So basically, again, this is just the recording of all the slopes of each x coordinate here, right? Because this is the derivative. So it would be really hard to do that. But what's easy is to sketch it by hand. The easy thing is to look up here and see, well, it looks like there's a slope of 0 right here. There's a slope of 0 right here. So I'm just going to look at this x coordinate. At that x coordinate, the slope is 0. So what you can do is just think of, I'm just going to drop this straight down to here. And right there is going to be a 0. So I know the curve is going through there. And likewise, right here is a 0. So I'm going to come right down here. That's a 0. So I know the derivative. This, when I sketch f prime of x, it's crossing the x-axis here and here because the slope is 0. So y equals 0, right? This is a collection of all the slopes. The derivative is a slope. So the way you can do this by hand is just think, okay, what about between this point and this point? Isn't it true that between those 2 points, the slope of every one of these tangents is negative? Right? So I start going here, they're negative, they get more and more negative. Then over here, they start to flatten out and approach 0. So like maybe the most negative slope is right here in the middle. So basically, the slope here is 0. If I go a little bit to the right, it's a small negative, right? So over here, a little to the right would be a small negative. If I go further to the right, it gets more steep, so it's a bigger negative number. So over here would be a more negative number. So if you think about what that's going to do, it'll go something like this, and then it comes back around, right? Because over here, probably the most negative right there. And again, we don't have these axes scaled, so we're just looking for the overall shape. So if somebody else draws theirs down like this, it's okay. It doesn't matter. I could do just as easily draw it like that. So maybe somebody else made it a little bit steeper. That's fine. It's just the shape that we're interested in. So you could even say like, yeah, I think it was a little bit more negative here. You know, it doesn't matter. It's the shape that we're interested in. And the idea that the slope is 0 here and the slope is 0 here of this, which means the derivative is 0 and the derivative here is 0. All the slopes of these tangents are negative, so they'll all have negative numbers here. These are all negative numbers, right? The y is negative. So then consider this point. This curve has a slope of 0 here, and as I go a little bit to the right, the slope becomes positive, and as I go further to the right, it's more and more positive. So that would mean that this branch would just start to come up, right? Something like this. And it just goes more and more positive. There's no, you know, it doesn't change here. At least we can't see that it changes. And then it's sort of similar over here. Like this is 0, the slope right here is 0. And if I go a little to the left, I start to get a positive slope. If I go more to the left, it's more and more positive. So you can see like this one's a little bit positive. Maybe when I'm at 0, it's more positive. If I go to the negative, it's even more positive, which means that if I plotted those points here, you know, I'd be plotting these and they would get more and more positive. Okay, so we've got f of x, f prime of x. You may have noticed something too. Doesn't this have a shape of like a cubic, like a third degree equation? And then what happened to this one? Looks more like maybe a second degree equation. Okay, so if we continue one more time, now we need to find y equals f double prime of x. Well, f double prime of x is just the derivative of this one. So we can continue the same thing. Like basically, f double prime is a collection of all the slopes to the tangents of this curve, of the tangents to this curve. So we could do the same sort of thing. Like right here, we can see that this slope is 0. Right, the slope is 0 there. So if I follow this right down here, I know that this graph has a 0 there because this is a measurement of all of the slopes here, right? Because this is a derivative of this function. Then if you look here, so the slope is 0 here. If I go a little to the right of that point, look what happens. I get a positive slope, a little more like more positive. So these tangents tend to become more and more positive, which means that this would be sort of like going more and more positive. It's going something like this. And then over here, it's the same thing, but I have a 0 here, but as I go this way, I'm getting these negative slopes, right? So if I go just to the left of this point, it's a little bit negative. I go further to the left, it's more and more negative. So if I record these slopes down here, I'm going to get these negative values. So they would be going more and more, so they'd be going something like this. So, and now these are hard to see, so I'm kind of leading you a little bit because we're saying this was a third degree. It looks like it could be a third degree. This looks like it could be a second degree equation, like a quadratic. Go down one more, it'd be like a first degree equation, like a line. So for this section, we just have to be able to sketch some of these curves, but the trick is to look where the graphs flatten out, where the slopes are 0, and drop those down. And that'll get you started. And again, we don't have to have the perfect, you know, the perfect values here. We just want the overall shape. So somebody else could have something that's a lot different because we're not measuring these, they're not scaled, but the shape should be similar. It should be something like this, then this would be more like a line. Okay, let's take a little practice, but you are in luck because we have one right here. Okay, everybody ready to try one? Here is y equals f of x, and your job is to sketch the graph of y equals f prime of x. So take a minute, just try this out, think about how you would do it, and then check back. All right, hope you guys are trying these out. So the easiest way to do one like this is to find out where these are 0. So I'm going to look for this 0 slope. So there's a slope of 0 there, 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 and there. So since this is a recording of all the slopes, I need to just start by putting these zeros down here, because that'd probably be the easiest way to go. So the 0 come down here, 0 come down here, and here, and here. So then the way we fill in the rest is we think of it like this. So between these 2 points, all of these tangents have negative slopes. So I'm going to have to record negative values down here. So the y values will be negative, right? You can sort of picture them even. So this slope here is a negative and becomes more. These tangents become more negative and more negative. And then they sort of flatten out again and become 0. So like maybe it does something like this. And then over here, between these two, these tangents are all positive, right? All positive. Starts off with 0, and then positive, and then ends up being 0 again. So it would go up something like this, go back to 0. And then these are all negative slopes. All these tangent lines have negative slopes. I know these are not the greatest drawings, but all negative, and then it ends up being 0 again here. So these will come down, a little bit negative, and come back up here. Now from this point on, these are all going to be positive slopes, right? So these are all, if I measure the slope of these tangents all have positive slopes. So this would just keep going up like this. Okay, so we just got a little bit left. So over here, looking at these slopes, these are all positive slopes, right? It's 0 here, but if I go in this direction, these slopes, the tangents become positive. It looks like it gets steeper and steeper as I go. So this would go something like this. Okay, so that is what we have to be able to do. If a graph of a function is given, we sketch a graph of the derivative. And again, everybody will get a little bit different. Maybe somebody comes down here, comes up here more. It doesn't matter. It's just a general shape. We should all have this general shape. Let's take a look at example 4. Example 4 says we've got this graph of f of x equals x cubed. And we want to sketch this graph and see if we can make a guess at the derivative. So with this one, if we're looking for where this flattens out, it sort of flattens out just at the origin, right? Just at the origin it flattens out. So we know this graph is going to go through here. And then if you notice, if I go to the right, and you start thinking about these tangents to the right. Aren't these tangents to the right, the slopes of the tangents all positive? But then also, the tangents to the left also are all positive. So the slopes are positive everywhere. So, and they get bigger, so it looks like it probably does something like this. So this is x cubed. What do you think this is? It looks like some sort of x squared, right? Maybe some sort of x squared? And if you don't know, which we don't just by looking, maybe I'm going to put an a here. Some constant x squared, right? Maybe it's a 1, and we're guessing, right? We don't know. We're just guessing. It looks like some sort of second degree equation coming from here. Well, luckily for us, we've got a way to figure this out. If f of x is x cubed, we can use a limit definition of a derivative to figure out what f prime of x is. So let's try it out. F prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we plug this in, we get the limit as h approaches 0. Okay, now remember, this is f of x. I need f of x plus h. So wherever I see an x, I'm going to put an x plus h. So we get the limit of x plus h cubed, right? That's f of x plus h, minus f of x. So there's f of x. So I go minus x cubed all over h. And then what we have to do is expand this one. We have to expand this. And I'm going to take a minute and show you a way to do the binomial expansion that's kind of easy. All right, so this is kind of a little aside here, and you don't need to write this in your notes. I'm gonna erase this in a minute. But let's just say we had a plus b to the 5th power. It's going to try to expand this. Now, the cubic is something you can look up. You know, there'll be an expansion for a 3rd degree, probably in the back of your calculus book. But I'm just going to show you kind of an easy way to do this. And the first time I do this, it looks sort of strange, but by the second time, you'll see it's a pretty easy pattern. So if I want to expand this, what you do is you start with the a and write it to the 5th. So whatever this first term is, put it to that power. And then this term, I'm going to write it in here in blue. This is the one you wouldn't typically write, but I'm going to put it here so we can see the pattern, b to the 0 power, which is just 1. So I'm putting it here just so we can see that these always are going to add up to 5, 5 plus 0. Okay, now to get the next term, what I do is I take this 5, and I multiply it by the coefficient in front of the a, which really is just a 1, right? So technically there's a 1. So you go 5 times 1 is 5. And I'm going to divide it by the location here. This is the first term. So I'm going to know 5 times 1 is 5, divided by 1 gives us 5. So you get plus 5. Now the a term drops by 1 and the b term goes up by 1. Okay, so this gets us here. And now I'm going to do the same thing. I'm going to multiply these. 4 times 5 is 20. And now I have 1, 2 locations. So I go 4 times 5 is 20. Divided by 1, 2 gives me 10. So I put a 10 here. The a goes down by 1. The b goes up by 1. Okay. So now we go 3 times 10 is 30. Divided by 1, 2, 3 is 10. So I go plus 10, a goes down by 1, b goes up by 1. And now I have 2 times 10 is 20, divided by 1, 2, 3, 4, gives me 5. You'll also start to notice the symmetry with the coefficients. A goes down by 1, b goes up by 1. So I guess I can put a 1 here just so we can see the pattern. So you notice these powers are always adding up to 5. And then finally we have 1 times 5, which is 5, divided by 1, 2, 3, 4, 5, which gives us 1, which is like this one here. So I won't actually write the 1, but a goes down by 1, so it's really a to the 0. So I'll put this in blue because it's one you typically wouldn't write. A to the 0, b goes up by 1, b to the 5th. So that's how you do the binomial expansion. And you just notice the numbers. So let me put these other numbers in here so we can see them. So you've got a 1 here and a 1 here. The powers all add up to 5. And you could sort of see the pattern with the powers here. And if this had been a minus, just whatever the b is, wrap it up with a minus. So it'd be negative b to the 0, negative b to the 1, which would make this be a minus here. Negative b squared would be a plus, so that'd be a plus. But then a negative b cubed would be negative b cubed, so you get a minus. So if there's a minus here, just do the same pattern and they'll work themselves out. So let's do one more. Let's just go put one with an even power. All right, so we start off the same thing, a to the 6. So I'm going to go a to the 6, b to the 0, so I just won't mention it, plus, I'm going to go 6 times 1 divided by 1, which gives us 6, a to the 5th, b to the 1. And then we have 5 times 6 is 30, divided by 1, 2 is 15. So we get plus 15, a to the 4th, b squared. Then we have 4 times 15 is 60, divided by 1, 2, 3, which gives us 20. A cubed, b cubed. And now we have 3 times 20 is 60, divided by 1, 2, 3, 4, which is 15. You can see the symmetry happening again with the coefficients. A squared, b to the 4th. 2 times 15 is 30, divided by 1, 2, 3, 4, 5, which gives us 6. A times b to the 5th. And then finally we have 1 times 6, which is 6, divided by 1, 2, 3, 4, 5, 6, which gives us 1. A to the 0, so it goes away, and then b to the 6. Okay, so that's just a little easy way to do Pascal's triangle, or actually to do a binomial expansion, but something slipped. Pascal's triangle, what? Let's look at Pascal's triangle, because you can use that here too. I'll do this. Okay, let me do this over here. So Pascal's triangle, you can use this here too. Pascal's triangle, if you start with a triangle like this, 1, 1, 1. So just start with this, and then I'm going to put another 1. But now what I'm going to do is add these two together. 1 plus 1 is 2. And then I end with a 1. So once again, I start with a 1. Now I add these. 1 plus 2 is 3. 2 plus 1 is 3, and then 1. And then I start with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then I end with a 1. I do one more in here. 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then you end with a 1. So these are the coefficients also. This is the coefficient here. If you do something like a plus b squared, you get those coefficients. This one's going to be a plus b cubed, a plus b to the 4th, a plus b to the 5th. See, do these look familiar? 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. And then you can keep going too to build up Pascal's triangle. But what I want to do is just see if we can remember this, how to find x plus 4 cubed. Give this a try. First, let's get all of this out of here. Erase all of this and see if we can continue our derivative problem with the limit definition of a derivative. All right, so to finish this up, we get equals the limit as h approaches 0. So you remember how to do this one? X cubed, right? So we'll get x cubed, which would be x cubed h to the 0 plus 3 times 1 is 3 divided by 1 is 3. X squared h to the 1. 2 times 3 is 6 divided by 1, 2 is 3. Plus 3x h squared. And then 1 times 3 is 3, divided by 1, 2, 3 is 1. X goes to x to the 0, so it goes away, plus h cubed. All right, now, in case you're wondering, you're not going to have to do this, okay? So don't worry about it. It's just a little extra. If you ever occasionally have to expand things, it's an easy way to do it. And then we also have minus x cubed. So we have minus x cubed. I mean, you're not going to have to do this in my class. I'm not going to make you memorize that or anything like that. It's just a little extra. Okay, so once this is expanded, we can look for things to cancel. You've got x cubed, and that's about it. So then we can write equals the limit as h approaches 0. 3x squared h plus 3x h squared plus h cubed all over h. We can cancel these h's. This becomes h to the 1, this becomes h squared, and that is gone. So we get the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now we take the limit, that h goes to 0, that h goes to 0, and the limit is just 3x squared. So the graph we were looking at for f prime of x, that we thought it looks something like some sort of square, we were right. And this limit definition of a derivative has shown us that the derivative of f of x equals x cubed. The derivative is actually 3x squared. Okay, time for a quick definition. A function f is differentiable at a if f prime of a exists. So it's differentiable at this point if the derivative exists at that point. And it's differentiable on an open interval, ab, if it is differentiable at every number in the interval. Okay, so basically this just means when this exists, it means that the limit exists, right? The limit is h approaches 0 of f of a plus h minus f of a all over h exists. So what we need to be concerned with is what could cause a function to not be differentiable. Because with calculus, we're going to be differentiating functions all the time, so we need to be aware of some of the cases where maybe a function doesn't have a derivative or doesn't have a derivative at a particular point. So that's what this next little part we'll talk about. So how can a function fail to be differentiable? Well, the graph has a corner or a kink. So meaning that the graph changes direction abruptly. When we try to compute the f prime of a, we'll find the left-hand limit does not equal the right-hand limit, which means that the limit doesn't exist, remember? So here's an example. An example would be, it's a function we've all seen before, y equals the absolute value of x. So you know that when we graph this one, you've all seen this graph, it basically just looks like this. Well, the problem is, if you blow up this area at the point, you know with a graphing calculator, typically as you zoom in on a point on a curve, the curve tends to flatten. It looks like it flattens because we're spreading out the area. Well, here, if you do that here, you can zoom on that point all you want. It never flattens. It's always pointy. So when you're trying to take the limit, so I mean, I guess we could, let's do this. If I take the limit as h approaches 0 from the right of f of x plus h minus f of x all over h. So as I'm approaching h from the right, the limit of this is going to be 1. But if I take the limit as h approaches 0 from the left of f of x plus h minus f of x all over h, so now I'm coming in this direction, that limit is a negative 1. So we're in this case right here. So the limit as h approaches 0 just does not exist. Geometrically, you can see it because you can blow up this area forever. It never flattens out. It's always pointy. Okay, so this would be called a corner or a kink. It's just like it's pointy. It's always going to stay pointy. So this function is not differentiable at that point. Another example could be something like this. If you have y equals negative 2 times x minus 1 to the 2/9. When you graph this one, it does something like this, where it goes like this. And again, if you blow up that area, it never flattens out. It's always pointy. So when something like this happens, the function is just not differentiable at these points. Okay. Also, the graph could have a discontinuity. So you could have something like this. So you have this graph that goes something like this. It comes down, and then it jumps up here and keeps going. Well, it's definitely not going to have a derivative here. It's not going to be differentiable here where there's this discontinuity like that. Or even you could have something like this. You could have a graph that goes like this, and it goes along, but it has a hole here. So even if a function is not defined just at a single point, then the function is not differentiable at that point. You could see that if you think of the definition, because in the definition we're going to have, it's going to be the limit as h approaches 0 of f of a plus h minus f of a. F of a, if this is a, f of a does not exist, so we can't use that limit. So if we have a hole in the graph, there's no derivative at that point. And then one more thing that could happen, the graph could have a vertical tangent. So as an example, let's say you have the function y equals the cube root of x. If you graph this one, it's sort of like x cubed, but on the other axis, so it goes like this. Well, there's a vertical tangent right here. So this function is not differentiable at 0. So generally speaking, if there is no tangent line, at a point and there is no derivative at the point. So if you can't imagine a tangent line being there, like if you try to think of a tangent line of the absolute value function, like how could you have a tangent at that point? You know what I mean? So when that happens, there's just not a derivative there. We do have a theorem. Also, a theorem says if f is differentiable at a, then it is continuous at a. This theorem says that differentiability implies continuity. So if a function is differentiable somewhere, then it's continuous there. But the converse is not true. The converse is not true. So we can say that differentiability implies continuity, but we can't reverse it. An example of that, why the converse is not true, is when we just looked at y equals the absolute value of x. This function is continuous everywhere, but it's not differentiable everywhere. Okay, so we can say that if a function is differentiable at a, it's continuous at a, but we can't take the converse. And then we have to talk about higher derivatives. So higher derivatives, I can tell you that normally for applications, you don't go beyond the second derivative. But when you will see them a lot is in Calc 2 when you're using Taylor and Maclaurin series. You'll go definitely take higher derivatives there for Taylor and Maclaurin. But some of the notation that you'll see is this. So we'll see something like y double prime for the second derivative, maybe y triple prime, or maybe you'd see f double prime of x for the second derivative, or f triple prime of x. You might see something like d squared y dx squared. And not too often, but maybe occasionally you'll see this. Now when x becomes, or when we're going beyond the third derivative, then we normally write something else. So beyond the third derivative, you'll see things like f, and then you'll see this 4 in parentheses. That's a fourth derivative, or the fifth derivative, something like that. It's typically what you see. And this notation is a little strange. So it's just if you have notation like Leibniz notation, like this, dy dx, then if you think of taking the derivative of it, you could say, okay, I'm going to take the derivative of that. So like the second derivative. And then it just sort of looks like d squared y or dx squared, like parentheses here. So that's why we have this sort of strange looking notation here. But you don't see this too much. Normally you'll see, when you have higher derivatives, you'll see this notation with f. You have f prime of x, f double prime of x, f triple prime of x. And after that, you'll see the numbers up here like that. And that brings us to the end of section 2.8. Most of the work in this section is really done in 2.7. 2.8 just has a couple of things. So definitely try the homework. As you know, that's the only way to get better at calculus is by doing the homework. And if you have any questions at all, just let me know.